All right, so just to give you a brief overview of these three grounding tables, right? So the 250.66 is your main service table, right?
R-
I mean, it's based off of a feeder wire because you don't have a breaker ahead of it. You can't, matter of fact, you can't have a breaker ahead of it. So if you have a question that tells you you've got a breaker and there's a wire feeding off that breaker, it cannot be Article 250.66. It has to be in front of any overcurrent protection device. OC,
Okay.
right? So
Right.
we're going to call that our earthing or our grounding, our service grounding conductor. And then the 250.122, which is the other main table, that's the one that's been around forever. That's your branch circuit stuff. That's your branch circuit is protection for shocks and equipment being over amped or over voltage. It's short circuit ground fault protection. And so that's the wire that's going to trip that breaker. And so those, because it is the wire that trips the mechanism and the breaker, is going to be based off that breaker size.
Okay.
So branch circuit based off of breaker size, and your service breaker or your service ground based off of your wire that goes in front of the first main overcurrent protection device. Okay. The 2.102C1, we'll talk about it in a minute. I'm going to just, for now, we're just going to kind of ignore it and just talk about these other two because these other two are fairly easy to kind of discuss. The 250.66, you're going to find it on page 116, and then I think page 125 for the other one. You might want to check and make sure that's correct.
Yes.
Okay. So page 116, 250.66, it's really simple. It's just the biggest service conductor in the service. And when I say service conductor, the biggest ungrounded phase conductor, hot, whatever you want to call it. Your black, your blue, brown, purple, yellow.
Right.
All right.
Now,
Now,
just any phase.
Yeah, any phase. Whatever the biggest one single phase wire is. So we base it off of wire size. All right. Copper is the first column, and then you have aluminum on the second column, and then you have copper and aluminum for your ground wire sizes themselves. And like I said in class, you got to be careful with this one because you always have to think and respond in copper, right? And so be careful of those questions. I'm not saying they do this, but be careful of those questions that may give you an aluminum feeder, but then ask you for a ground wire size. Because if the aluminum feeder is given to you, if they want you to answer in aluminum, they also have to specify that they want the ground wire itself sized in aluminum as well. Make sense?
Okay.
So,
Yes.
for example, they could give me a 250 kC mill and not tell me what it is. I would assume in that case that it's copper, right?
Right.
250 kC mill copper would be what, about the third line down, I think? 3 up,
Yes.
250 on that very first column. How about that from
Yes.
memory? Come on now, from memory?
That's amazing how much you
I'm surprised I can remember the page number, much less that specific of it. But at any rate, and then what do you see for the copper ground wire size on the third column?
It's number 2.
All right, so that would be your size based off of that ungrounded conductor. Now, if they were to tell me that I'm running aluminum on my ground wire, on my feeders, that's going to change my answer only because of the fact that the 250 kC mill aluminum, if you look in the second column, is actually going to be one row further up from where you just were, right?
Yeah.
So it's going to give you what as an answer?
4.
Is that number 4 copper?
Copper.
Correct. So I'm going to still answer in copper, right?
Right.
Even though what you're giving me in my feeder is aluminum, because again, if they want me to answer in aluminum, they have to specifically say, I want to know what it is sized in aluminum.
Okay.
Okay? All right. So I'm not saying that they do that, but I'm not saying they don't do that because it's just a real simple.
Right.
They make a real big deal about telling you, thinking copper, thinking copper, thinking copper. It's always copper unless they specifically say, I want my answer in aluminum. Just be careful of that.
Okay.
And I promise you, it's little stuff like that that cause more problems on this test than you have any idea. You know?
The questions are tricky. They like to trick you.
Yeah, right. So you just have to pay careful attention. Other than that, it's not a real complicated table. I mean, it's really simple. Now, it gets a little bit more complicated when you get into parallel, right? However,
Right.
the nice thing about this table is that if you look at the bottom row says anything over 1100 kc mil is simply a 3-hot. Well,
Right.
okay, that just means that I could have a wire size that's 2000 kc mil, technically, right? So 2000 kc mil, if I had a wire size, if I was stupid enough to try to run a copper wire that big, I can't even imagine how much that would weigh. God, that would be a heavy son of a gun. Oh my God.
That'd be tricky.
You ever tried to lift or install 1000 kc mil copper conductor?
No, the biggest I've done is 750.
Yeah. I did it one time, and I remember it to this day. I hurt for weeks. I felt bruised all over, and it took 11 of us to move the thing around. Anyway, all right, 2000 kc mil copper conductor, right? Well, where does that fit on the table? Is it over 1100 kc mil?
It's over.
I'm still only going to have a 3-aught. I mean, that's.
3-aught.
I mean, I'm capped at that number. I don't ever go bigger than that.
Okay.
That makes sense?
Yes, sir.
All right, so that's the nice thing about it. I don't have to worry about anything over that. I mean, once I get 1100 and above, it's always going to be a 3-aught. That's the maximum size. Now, where it does get a little tricky is, all right, well, what if we have parallel conductors? Think about it like this. Go to page 150 and tell me what wire size would I have to have if I wanted to have a 750 amp load, right? Go to page 150 and tell me what wire size would I need under the 75-degree column to carry 750 amps. There's not one on there, is there?
No, the biggest
Like
665.
500 something amps or something at the most.
Yeah, 665 is the biggest.
I'm teaching. Okay, I love you. Come here, give me a hug. Give me a hug. You look so cute. Come here. Come here. Come here. Come here. Look at that. Look at that cutie.
Aw,
Say
how
hello.
cute.
Say hello. Oh, it's okay. No big deal. Just trash. Say hello.
How are you?
All right, go to church. I love you. Watch out for mama. Make sure mama behaves, okay? Okay. Sorry about that. All right, so I'm 750 amps. I'd have to have parallel set of conductors, right? I'd have to have at least 2. Let me make it a little bit more realistic. Let's just say that we're trying to do 500 amps. What wire size could I get away with 500 amps?
900.
So 900 kc mil would be good for what is it?
For 5.
Is it what?
520.
520? All right, 520 amps. Well, the funny thing about wire, when you're running AC current through it, and I had somebody once tell me, even Nikola Tesla said, sometime in his career, I don't understand electricity. Nobody understands electricity. We have no idea what this stuff is, what it does, how it works. I mean, the only way we know anything about electricity is we've tried to hook stuff up, and when it blew up, we go, that didn't work. Let's try something different, right? So, but this is an interesting thing, and it's kind of, to me, it's always been something that's stuck in my mind. When you take a conductor and you run AC current through it, right? What happens is that all of the electron flow actually occurs in the outside edges. It's just the way that the magnetic flux lines happen. So if you're looking at a conductor that's a really large conductor like that, the center core of it doesn't really get much activity at all. And so if you start looking at them, what's the wire ampacity for a 2000 kc mil conductor?
665.
So it's really not that many more amps, is it?
No.
You more than double the size of conductor and got 145 amps worth of wire capacity out of it. Basically the same amount as a 1-aught would give you. And you doubled it by more than 1,100 kc mil. At some point you just lose much traction when you get into larger wire sizes. So it's better to start paralleling them.
Right.
The smaller the wire, the less of this unused core you're going to have in the middle of an AC circuit or an AC running on a wire. Okay, I'm telling you all that just to kind of give you a little background. Well, for me, it kind of makes sense because then it kind of made me understand some of this a little bit better. But at any rate, so you're understanding a value of 500 amps. I could either do one set of 900 kc mil, or you know what? I'm going to be smart. I'm going to take this 500 amps and I'm going to run 2 wires, which means I'm going to divide that by 2 and go, okay, I need a wire that'll only carry 250 amps, but I'm going to have 2 sets of them. Huh? Okay. See? Mama didn't raise no dumb electrician, right? Now,
right.
Look on your 75 degree column. What can I use for 250 amps?
250.
Okay, so I could run a pair of 250s combined that's less than 900, isn't it?
Right.
I mean, but still, I mean, I'm basically saying, okay, I'm going to have an A over here, and I'm going to have an A over here. I'm going to run them in parallel pipes probably, and combined, each one of those is going to be a 250 kc mil. Or excuse me, not combined, but each one separately, right? 250
right.
kc mil. You understand what's happening, right? We're splitting the wire because the single wire doesn't really carry that much amp. So we're splitting it in. We're basically taking the demand load we have there and splitting it into 2 wires. Well,
correct.
Go back and look at this table. And the reason why I'm telling you that is this table is based off of what? One single wire, right?
Yes.
Okay, well, if I'm running a single wire that's a 900 kc mil versus 2 wires that are 250 kc mil each, well, I got to figure out how to do the math to get it back in some relationship. So if I were to go down and go, okay, well, I'm using that table and I had a 900 kc mil, what wire size would that give me on a ground wire, copper wise?
That'd be 2-aught copper.
2-aught copper, okay, right? Well, like I said, Mama didn't raise no dummy, so I'm not going to do that because number 1, it'll kill me to try to install. Number 2, the cost of it will be just ridiculous. And number 3, look at the amount of ampacity I get for wire that's not even quite that size, right? So,
right.
All right, well, how do I relate these 250 kc mils up here? How do I relate these things to the single wire I had a minute ago? How do these two relate to each other? Well, note 1 down at the bottom says, okay, well, if you split parallel sets, then the corresponding conductors of each set have to be added back together. And basically what we're doing is we're just recombining them so we get the same equivalent wire size to then go back to the table with, right? And that's all we're doing. We split them to save on the ampacity, but now we got to recombine them to get the proper ground wire size is what I'm getting at. So I go over here and go, okay, well, if I've got 2 sets, and what I'm talking about is I've got a pipe over here with an A, a B, and a C, right? And over here I've got the exact same pipe with the exact same conductors in them, because remember, parallel have to be the same size, same material, same insulation, same length. I mean, everything has to be exactly the same, right? So I know that whatever I've got over here is going to be the exact same thing right next door. So I'm just going to talk about just this one. So what I'm going to do is I'm going to take the corresponding conductors of the A phase, which is going to be this one and this one. And I'm going to go, okay, I've actually got 50 kc mil, but I've really got 2 of those. So I'm going to multiply that times 2. So what I did was I recombined them into 1 wire size, and now I've got a single equivalent of a 500 kc mil. Then I go back to the table, and what ground wire would that be?
That'd be 1-aught copper.
1-aught. So I'd size that as a 1-aught copper conductor. And it's a little smaller than if I ran a single wire, but that's effectively the way it is. And I would have a 1-aught in each one of these pipes. So I would have more than just a 1-aught. I'd have 1 in each parallel set, but that's how that works. If I were to have 3 parallel sets of 250, 4 parallel sets of 250, 5 parallel sets, how many I change this number based off the corresponding numbers that I have.
Okay.
So if there's 4, it'd be 4 times 4. If there's 5, it'd be times 5, whatever. Okay?
That makes sense.
Yeah, I mean, for a long time, I calculated it differently because the way I read that was the corresponding conductors of each set. If you ask me, a set is this.
Right, the whole pipe.
But corresponding conductors, I mean, I can't say that an A and a B and a C are corresponding unless I'm talking about the set, a 3-phase, but that's really not what they're talking about. they're talking about the corresponding conductors of each set, meaning the corresponding conductor of A in that set, the corresponding conductor of A in the next set, the set of those A's together is what they're talking about. So it's not written very well or very clearly, but that's what they mean.
Okay.
Okay. So now remember, there cannot be a breaker ahead of that. So, I mean, occasionally you'll see a setup like that, but not every day. I mean, usually you've got one set of conductors, maybe a parallel set of feeders coming in. I mean, we don't typically run ground wires in our feeders coming from the utility anyway. I mean, that's very rare.
Right.
So, I mean, it's not the most common thing, but if you're inside your distribution and you're inside your master or something inside, coming down the riser or maybe underground or something, you might run up ground for whatever reason. But it's like I said, it's not very commonly done. But anyway, that's okay.
Okay.
Wouldn't be any different if it was aluminum. Same thing, just different second column instead of the first column. So I wouldn't do anything different on that. So if I had 5 parallel sets of parallel conductors, so we'll say 5 sets of 3/0 copper conductors, and I'm going to say these are 3-phase, not that it really matters. What would be the ground wire required in each one of those parallel sets? Okay. You want to try this one on your own? Or you want me to walk you through it?
Can you walk me through it? Just but the only thing that throws me off is 3/0.
I know. I figured it might. Where in your code book? Now remember, a 4/0 all the way down to 14 gauge, anything in between that. Remember, that's just an American wire gauge, and an American wire gauge is only a label. Got no mathematical quality to it at all whatsoever. I can't take a 3/0 and divide it by 3 and get 1/0. I can't multiply it times 3 and get a 9/0, right? It's got no mathematical value. So anytime I have an American wire gauge, anything that's 14 gauge to 4/0, I have to convert it to circular mills before I can do any math to it, right?
Right.
Where in your code book is there a conversion table that gives you circular mills? Do you remember?
I don't remember.
Page 676. I think. I hope. It's table 8 in chapter 9.
It's not 76.
God dang it. 676. Chapter 8. Right after chapter 5A. Should have a tab for it if you got our tabs. Very top says chapter 8, yellow tab at the top.
Chapter 8. 690 or 689.
689. That's what I said. That's what I've got written down there, right there. It says 689. I have to get the eraser. Okay. 689. All right. So you'll notice that the third column on that table is circular mills.
Right.
And it goes all the way to 4/0, and then it becomes blank because we already call after that, after 4/0, 250 kC mill is 250,000 circular mills, so it's kind of redundant. Okay.
Okay.
All right. So we're at what do you have there on that table then for 3/0 copper?
167,800.
167,800. Now remember, that's circular mills. That's the equivalent of a 3/0, right? So all we did was convert that to that number mathematically. Now, I've got an A, an A, an A, an A, and an A. So I'm going to take that number times 5. So let's see here. Luckily, I brought myself a calculator. 167,800 times 5 gives me 839,000 circular mills. Same thing as an 839 KC mill, right?
Right.
Now, all I did was I just combined those phase conductors into one equivalent. That's all I did. Now I'm going to take this and go back to page 116 and go back to the table and use that wire size to find my spot on the table.
So it'd be a 2-aught copper.
And that would be the wire size that I'd have in each. I'd have a 2-aught in each one of those 5 pipes.
Okay.
Okay.
Okay. That makes
The only difference
sense.
is there. Yeah, the only difference there is you had to convert your own wire size. No problem. Big deal. You got that. Okay.
Yes, sir.
All right. So that's that table. Now the other table we're going to go talk about real quick is just real simple. 250.122. You won't see it as much on the master's test as you'll see the other table that I mentioned briefly, which we'll get to in just a second. But 250.122, just so that we can cover it, on page 125, it's based off of breaker size. So once you get past a row, for example, you have a, 15 amp and then 20 amp, is it?
Yes.
And then it jumps to 60 amps, right?
Right.
Once you get past one row, you're in the next row all the way down. So in other words, any breaker size is 25 amps, 30, 35, 40, 45, 50, or 60. All of those are standard sizes. All of those would be on the 60 amp row. Be a number 10. The number 10, I think, right?
What? It cut out there.
I said, is that number 10? Right? Yeah. So anything 25 amps to 60 amps would all be a number 10. Next row, which is what, 100?
100.
So that would be basically anything that's 70 amps to 100 would be the next row, which is number 8, so on and so forth, all the way down the table. Okay?
Right.
It's not a complicated table. What if I had the same 5 parallel sets of feeders coming off of a breaker? So I've got these all coming off of one main breaker. We'll say that main breaker is rated for 1,000 amps. And these are all 250 KC mill conductors. This table is always based off of the breaker size, not the wire size. So I couldn't care less what they tell me the wire size is. It doesn't matter. Okay? If it comes after a breaker, I no longer care about the wire. And sometimes you'll see on the test question, they'll put the breaker and the wire size in there just to confuse you. If that wire follows after the breaker, it's the breaker that counts, not the wire. Okay? So what do you see on the row for a 1,000 amp breaker?
2-aught.
I'd have a 2-aught then in each one of those parallel sets. There's no math. There's no derates. There's no adding anything together. It's a full size in each one of those parallel runs.
Okay.
So for this table, no discounts, no derates, no fuzzy math. It's simply stick a full size in each raceway. All right? That was easy. I wish the other ones were that easy. The hardest one, I think, is 250.102C1. That's on page 119.
119.
Oh, yes. At least I got that page right. Page 689. You got a weird edition code book. They moved that page on me. I'm not sure when. All right. Page 119. This one's a little trickier. Okay. You know, it looks a lot like the one that we just looked at in .66, doesn't it?
Mm-hmm.
I mean, it almost looks identical. It's based off of a wire size. I mean, it's pretty much the same table. The only difference is the bottom row has some cryptic C note 1 and 2. So what that means to you is the other table had a maximum of a 3-aught. Didn't matter what it got to be. After 1,100 KC mill, from there on, it was only a 3-aught no matter what. This one's not that way. This one you got to be careful because there's a little bit of math involved, so you kind of have to be careful. Now, let's start simple. Let's just look at a couple of real simple examples. Let's say that we had just parallel sets, and I'm giving you parallel sets because that's what I'm seeing on these master's tests or hearing back about more than anything else is parallel sets when this table's involved. They're typically asking you for some kind of a bonding jumper or some sort of a jumper. Okay.
Okay.
So if you see that keyword, the word jumper, and they're asking you to size a wire that's a grounding conductor or ground conductor or some ground, that's the table you should be on, okay? You wouldn't use either one of the other tables to size any jumpers, but all jumpers would be on this table. Okay. So I got 3 parallel sets. Same thing, I got, let's say the 250 kc mill example we had a minute ago. So I've got an A and a B and a C in each one of these 3 sets. Each one of them is identical. So I go, okay, crap, now what do I do? Well, down at note 1 or down at note 2, I'm not sure which one, it basically tells you the same thing. You take the corresponding conductors of each set. When they're running parallel, you add them together and then use the table or use that 1 wire size to size the table. So it doesn't really change from that perspective. I'm going to take 250 kc mill. And I'm going to say, okay, the corresponding conductors of each one of these sets would be an A, an A, and an A, right?
Right.
So that's 250 times 3 because I've got 3 sets. That's a 750 kc mill conductor. I would take that wire size. Remember what I did was I just artificially added them back so that I could figure out where I was at on the table, right? But I still go back to the table to actually pick the ground wire size. So I go to 750 kc mill on the first column there, and what do you have for the ground wire size?
2-aught.
All right, so I'd have a 2-aught. And again, it's a 2-aught in each one of those runs, okay? 2-aught, 2-aught, 2-aught. Easy,
okay.
Right?
Mm-hmm.
It doesn't get any more difficult if they're the same example I gave you a minute ago, if they're 3-aughts, right? The only difference with a 3-aught or 4-aught or a 2-aught or anything that size, basically you can't parallel conductors under 1-aught, right? So it's common or expected on a test that you might see a 1-aught, a 2-aught, a 3-aught, or a 4-aught in parallel. Because those are the wires that you have to convert from an AWG to an actual circular mills, right? But no problem.
Right.
All you got to remember is page 6, what?
89.
Okay, all you got to do is remember that. Anything that's a 1-aught, a 2-aught, a 3-aught, 4-aught, run in parallel, and you're trying to size a jumper, all you got to do is, okay, no sweat. I'm going to go to page 689 because each one of these wire sizes have to be converted to circular mills before I can do any math. Okay? All right, so no problem. We got this problem on this test question. It gave me 4 sets of 2-aught. These are 3-phase feeders coming off of a transformer somewhere in a distribution system, going from the transformer into that first overcurrent device. I don't have a main breaker ahead of it because remember, off a secondary to transformer, there's no breaker ahead of it. I mean, breaker's at the end of the wire, right? So I can't use table .122 to size that because I don't have a breaker in front of it. So I use this table. It's a supplied side bonding jumper or system bonding jumper or supply side bonding jumper. All right. So in that case, I've got an A, a B, and a C. Each one of those is a 2-aught, but I've got 4 sets of them, right? So I've got 1, 2, 3, 4, all of those A's, and then of course I've got corresponding B's and C's, so on and so forth. So to do this, I got to take 2-aught and multiply it times 4. That'd give me what, an 8-aught? Right? Doesn't even make sense, does it? Go to page 689. Yep.
689. And it's 133,100.
There you go. That make you feel a little bit more comfortable about this?
Yes.
All right, so that's all the mystery there is to it. Then I just multiply that 133,100 times 4. That gives me 532,400. Now remember, again, just like all the examples we've done so far, what we just did is all we did was try to find the one ungrounded conductor that we would go back to the table to then find the ground wire size, right?
Right.
So go back to page 119 and use this 532 to find your place on the table. That's it.
Mm-hmm.
And where does that put you?
It'll be
a 1-aught?
1-aught.
Okay.
Yeah.
I have 1-aught in each one of those up there based off of that. Okay? All right. So far, so good. The only thing that's a little confusing, if you look at that table, remember, what's the last row say? What wire size fits on that last row?
It just doesn't have it. It says C note 1 and 2, and then I have times 0.125 beside
I know,
it.
but what's the wire size that row says? Over there on that very first column there, that bottom row, what's it say?
Over 1,100.
Not 1100 plus, over 1100, right?
Right.
So 1100 would actually be what, on the second to the bottom row?
Yes.
Okay. So anything more than 1100, so 1100 plus, okay? And I want to remind you that when we're talking about 1100, we're actually talking about 1,100,000 circular mills, okay? Sometimes guys forget that because we're talking about 1100, but we're really talking about add 3 zeros to every one of those wire sizes.
Okay.
250K, the K in the KC mill stands for that. So if I take the K off and just talk about circular mills, I have to add those 3 zeros back to that wire size. Just because if you don't do that, it'll be really easy to get your math kind of twisted, okay?
Okay.
I mean, you might be able to do it without adding the 3 zeros. For me, it's safer just to convert it to million square circular mills than it is to try to keep track of it otherwise. But at any rate, all right, now, why am I telling you this? Well, let's say that we have four parallel sets, but each one of those is a 750 KC mill. Well, now you got a problem, because when I take 750 and I multiply that times 4, right, that's going to give me a wire that went off the chart. So 750 times 4, I should be able to do that in my head because it's basically 12 quarters, 3 million. So my calculator, if I take 750 times 4, it's going to give me 3,000, but that's actually 3 million, right?
Right.
That's actually 750,000. All right. We're on the same page. Now, here's the problem. The math in note 2 or note 1 there says that I can't have anything less than 12.5% of this number right here as a ground wire size. So in this case, we're no longer trying to find the fake wire size. What we're trying to now find is the actual ground wire size. And that's the thing that confuses a lot of guys. So this time when we're done with the circular mills, we're actually sizing the ground wire with our answer. We're off the table. Once we get in that last row, there's no more ground wires listed there. So we're actually calculating the ground wire size now. So that 12.5% is that number times 0.125, because 12.5% is moving that decimal over 2 places. So it's 0.125. And if you didn't write that down on the bottom of your table the other day, please do so now, just so that you don't accidentally do 1.25, which is a very common mistake because we use that all the time for continuous duty. Looks like the same number, but it's way different. It's 12.5%, not 125%. Okay, so I'm going to take 3 million. So 3 million. I got to count the zeros, make sure I got it right. Multiply that times 0.125, and I get 375,000 circular mills. What I just calculated is the minimum amount of mass the ground wire has to have. So what wire size measures up with that? Well, if you're not sure, go back to page 689 and find the next larger size that's got at least that amount of circular mills in it. Be what, 400, I think?
Yes.
So I'd have to have a 400 KC mill as a minimum supply side bonding jumper.
Okay.
That makes sense?
Mm-hmm. Yeah.
Oh, man. That one is probably the trickiest part because you're not sizing you're not adding all this stuff to go back to the table because you're off the table. That's the one thing.
Right.
So you're actually calculating your own. If you use that 12.5%, that's the actual ground wire you're calculating at that point.
Okay.
Okay. All right. I'm going to call that good because I don't want to confuse you. If you can remember those examples and just kind of keep that straight, you'll be fine. If you get a smaller wire size, go back to page 689, convert it to circular mills, do the math. If you're on the table, you're on the table. If you're on the first table, remember, it doesn't matter. It's a 3/0 no matter how big that wire size gets. So that could have been a 3 million KC mill on the first table. Wouldn't have mattered a bit. It'd be a 3/0.
Right.
Okay. It's just this one because of that 12.5%. Okay. Woo! Feel better about those?
Yes, much better.
Okay. Let's get off that subject and go talk about some service calculations, and then we'll come back and do just a couple of quick ones just to make sure it's sunk in. Okay? All right. He's like, dang it, I thought I was done with that. I don't want to see those. Yes. All right. Services. What do you want to know about it? If it's residential, put a 200 amp. If it's commercial, put a 400 amp. Done.
I wish it was that easy.
I had somebody tell me that once. They were trying to argue. They're like, I don't know why I got to calculate this. We always put a 200 amp on electrical service for residential dwelling. Ain't never gonna find nothing else with 200 amps on one anyway. Yeah, they're practically correct 99% of the time. All right. When it comes to calculations, service calculations, there's two worlds. We got residential, and funny thing is about this code book is it's residential, it's residential, it's residential, it's residential, and then everything else. It's not residential. You know what I'm saying?
Right.
That's not residential. That's literally the way this code is written. So, I mean, you got to look at it like most of these calculations that we deal with in Article 220, and that's really where we're at with most service calculations. Most of the stuff in Article 220 is residential. I mean, almost every table that's in there except for one is residential. I'm sorry. I take that back. In the first part, the first part's there. Once you get in the optional method, there's another table that's for other things. But if you're in the standard method calculation, the first part of Article 220, it's mostly residential except for one table. So that's what I mean. It's basically written for residential, and then, oh yeah, by the way, if you get something else, deal with it, however, right? So that took me a while to kind of figure that out as an electrician, because I kept thinking, well, golly, I mean, if they got all these specifics about residential, commercial is even worse. Where's all the tables for commercial? I mean, what if I had a commercial occupancy, a commercial load, and I'm doing an office building, right? And they're telling me I got all these square feet. Okay, well, I can calculate that. I got no problem with that. They're telling me I've got all these, plugged in loads over here and this, that, and the other. What if they had let's say they had a break room, and maybe it was they had a little laundry facility so people could do their own laundry after they worked out in their little gym they had there, and they had 8 dryers in that laundry room, and each one of those dryers was 5,500 watts. And I get this on a test. I'm like, okay, how do I calculate 8 dryers that are 5,500 watts in a commercial building? Go. I mean, where would you find that in the code book?
I would probably try to go to dryers, but that's for residential.
Exactly. Go to page. Let's look at dryers. 220.54. There's a table on the right-hand side of page 71. 72?
73.
I was getting there. One more page I'd have had it. Page 73. On the top of that, you need to write really big residential only. You cannot use that for commercial dryers. Sorry. So where's the table for commercial dryers? There's got to be one. I mean, if we got a table for dryers for residential, where's the one for commercial? Not one.
There's probably not.
There's not one. If I got 5,500 watts and I've got 8 of them in a commercial building, I've got 5,500 times 8. That's it. There's no D-rate. There's no diversification. There's no increase. I mean, it's just, I got 5,500 times 8, and that's what I'm putting on my calculations for my feeder size. You see what I'm saying?
Okay.
So commercials really like that. I mean, whatever you got, you calculate that, right? Now, there are a few things that we look at, things that are continuous duty, like if we had lighting in a commercial building, those are going to be on for 3 hours or longer, so we're going to do the 125% for the lighting load. So there is not a decrease, not a derating, but an increase or an uprating, if you will, for continuous duty. So a lot of times with commercial loads, they get bigger instead of smaller like they do with residential, right? Mm-hmm. The biggest thing you got to remember, though, and this is one of the most key words to have in the front of your mind on this master's test in Texas, when it comes to any service calculations, you have to remember the difference between these two terms: a connected load and a demand load. Those two terms are absolutely critical. And depending on which one of those they ask you, you could have two totally different answers. Each one of them would be right in their own respective, just depending on which one they're asking you for, right?
Right.
Connected loads. Look at it this way. If I calculate a raw calculation, like the one I just did a minute ago when I had 8 times 5,500 watts, right? I mean, I'm not going to have any derating to apply. So that equipment rating or the nameplate of those dryers is a connected load. I don't have any derating to apply. So in this case, since there is no derating, my answer is going to be the same as my connected load. So those would be the same number. There's no derating table to apply. They're not continuous duty because they're not going to be in operation for 3 hours or longer. Now, they individually, they might be on and off at certain times, but I'm not going to collectively consider them continuous duty. So we're just going to leave them just like that. So in that case, the demand load and the connect load are the same thing. However, what if they were residential dryers? If these were residential dryers, well, we do have a table for those. And in a residential location, if I had 8 dryers, I'm really expecting that they probably won't all be on at the same time. Now, it's hard to imagine where you'd have 8 dryers in the same residential occupancy. I get it. But if there were some extreme example that you can imagine, well, I would expect that in a residential load, I've got some people that work during the day, some people that work at night, some people wash their clothes on Wednesdays, some people wash their clothes on Fridays, some people don't wash their clothes at all. Or very often, right? They'll take them out and let the laundromat do them. So how do I get this connected load, which is 8 times 5,500 watts? And let's just calculate that out. 8 times 5,500, that'd be 44,000. How do I get that into some realistic number that I think might actually happen? How do I take in that, people being off on different days and doing their laundry at different times of the day? How do I make that something more realistic? Well, I apply a derating factor. And a derating factor can be from different places. In this case, on the table on page 73, 220.54, that is a list of derating factors that would be applied to residential dryers. So if I had 8 of them, what do you have on the row that would have 8?
60. So
that's a percentage. That's 60 as a factor. That's 60%. If I move that decimal over 2 places, that's 0.60 as a calculation. So what I'm saying is the derating factor that would give me the demand load, and the demand load is that real world number that I'm actually using to size my feeders and my branch circuits and breaker size and all that stuff on. So I'm going to take, not branch circuit, I said that wrong, feeders and overcurrent device size and whatnot. So 60% of 44,000 gives me 26,400. Those are 2 correct numbers. I mean, one of them would be, in the case of commercial, that would be the same for both because there wouldn't be any derating. But in residential, I have a connected load that's basically the nameplate times 8, times how many I have. And then after I apply the derating factor that's found on the table, that's my demand load, the 26,400. You have to be careful because on this test, they could give you those 8 dryers in a residential dwelling and ask you what the connected load is. My answer would be 44,000, right? But if they asked me the same, if they gave me 8 dryers in a residential dwelling and said, what's your connected load for those 8 dryers? My answer would be 44,000 because the connected load doesn't have any derating factor applied to it. Most likely, and realistically, they're going to be asking you for the demand load because that's what we typically want, right? So the demand load would be after I apply whatever the derating factors are, 26,400. Okay? Now, since we're talking about dryers, let's just talk about dryers. That's a weird table, right? It goes 1 dryer is 1 through 4 dryers, right?
Yes.
100%. And then it goes on and gives you a bunch of other ones, but then it gets down to the bottom of the table. It says 11 dryers equals 47%. And you're going, now, wait a minute. How does that guy remember that? The next row goes, okay, well, let's see. 12 through 23, and I literally remember this, is 47% minus 1% for each extra dryer that's beyond 11. It's not exactly what it says, but basically what they're saying is you go past 11. At 11, you had 47%. And they're just basically saying, okay, the 12th one would be minus 1%. So 12 would equal 46. 13 would equal 45. 14 would equal 44. I mean, on and on and on. I'm just basically dropping 1%. They got lazy. They didn't have space for that big of a table, so they just said, okay, let's condense that into anything 11 or 12 through 23. Just take 1% off for anything past 11. Off of the line item that you left when you had 11. Real simple, right? So what if I had 21 dryers in a residential dwelling? What would be your connected load?
You'd have to.
Oh, crap. I forgot to tell you what the rating was. Well, let's say they're 4,500 watts.
Well, they have to be 5,000.
You caught me. Okay, you're right. To use that table, I have to use a minimum of 5,000 for any dryer I calculate under it, okay? So you're correct. So you caught that part. All right, so I got 21 times 5,000 watts. Watts, sorry. 21 times 5,000. 105,000 watts. That's a connected load, right?
Right.
What's my demand load? Well, you got to do a little work to get that. Because your demand factor, you have to calculate yourself. But no problem. How many dryers is 21 from 11?
10.
Okay. And each one of those 10 cost me a 1% drop from the 47% that the 11 dryers landed on. So this 11 was equal to 47. Each one of those 10 additional ones is minus 1%. So 10 times 1% is minus 10% basically. So I'm left with a minus 37%, right?
Right.
That's my demand factor. Just take your 1,000 times 0.37 and there you go. I had to do a little work to get my demand factor is all it was. But once I got it, then I go back and just multiply it times the connected load. So 105 times 0.37 would give me, oops, what was that? I don't know what that was. Just calculated something weird. 105 times 0.37, oops, dang it. 0.37, not 0.35. 850 is what I got. If I didn't mess it up too bad. No? Do you have something different?
No, I got that.
Okay. You don't you scare me like that. All right, now. Well, what if you had 41 dryers? Now what? Well, okay, it gets a little bit more complicated, but it's not that bad. You don't have to do the 12 through 23, okay? That's already been done. If you notice, the 12 through 23 row ended at 35%. Do you see that?
Mm-hmm.
Because if you think about it, if I had 23 dryers, the difference between 11 and 23 is going to be what? 12, right?
Yes.
So 47% minus 12% is what? 35%. So what happened is that when you got to that 23rd dryer, that 35% already calculated in all those steps above it, right? So I just keep on going. I don't have to stop and do that middle part. It's already calculated. I'm simply going to be, if I have 41 dryers, that's in that next row down, and it's going to be 0.5% off of the 35% that I just left that other row on. That's all it is. Anything past 23. So anything past 23 dryers then is going to be 0.5% subtracted from 35%. Okay?
Mm-hmm.
So, again, the 47% minus the 12% gave us the 35%. So, I mean, all of that jives. I mean, if you do the math, the table kind of makes sense. All right, so I would go, okay, well, 41 dryers minus 23 dryers is how many? I think it's 18. Let me double check.
18.
18. All right, so each one of those dryers is now, instead of 1%, it's 0.5%. So times 0.5%. So 18 times 0.5% would be 9.
9.
And I'm going to take that 9% from that 35. So it'd be 35% minus 9% gives me 26%. Now that would be my calculated demand load for 41 dryers. So if that were actually calculating the demand load, then I got one more step because I'd have to go back to say, okay, 41 dryers. Let's say they didn't tell me the nameplate, so I'm going to just use 5,000 as a minimum value. So I'd take 41 times 5,000, for example, and that would give me a connected load of 205,000 total watts, right?
Right.
I calculated out my new demand load at 26%, so multiply that times 0.26, and that would give me a total of 53,300 VA. What if they asked me for the demand load on the neutral conductor? How do you calculate a neutral conductor for residential dwellings? So there's just one more step. If you go look at 220.61,
All right.
starts on page 73, I think, at the bottom, and then continues on to page 74, I believe. No, page 75.
Mm-hmm.
It continues on the left-hand column, page 75, under A and B, where it starts talking about the maximum balance load on the neutral conductor shall be, yada, yada. And the A section says not less than 70% of the calculated value for the table 220.54 or 220.55, which is your dryers and your ranges. So what I'm getting at is that if I'm calculating a neutral for a dryer or a range, I'm using 70%. And I got that from 220.61A. Did you find that? I want to make sure that's right. I think that is. I'm doing it, like I said, from memory, but
Yes.
Okay. All right. It's kind of worded kind of funny, but it's 70% of. Can't use it. You can't calculate air conditioner loads, heating loads, but you can do ranges and dryers under that section.
Okay.
So it'd be 53,300 volt amps on the phase conductors, and if they asked me for a neutral calculation, it would be that 53,300 times 0.70. Okay. Now, I only point that out because there's been some rumblings about something similar to that. So neutral calculations for dryers or ranges, just take one more step, 70%, whatever your calculated load is. I mean, your demand load, excuse me. Man, I feel like you know this stuff now. How do you feel? Ready for this test?
Yeah.
What? Right?
Yeah.
So remember with service calculations, you get the standard method when we're talking about residential dwellings. We also have the optional method. The optional method is really referring to either 220.82 or 220.84, depending on whether or not you're talking about single-family dwellings or multiple-family dwellings. 220.82b is the section that calculates, well, it's B and C, I should say, which calculates the optional method for a single-family dwelling. 220.84c calculates multifamily dwellings. There are two different methods. You can't use the optional method unless they specifically tell you to use the optional method. I would like to point out that basically everything from 220.60 and forward, all the way back to the beginning of the article, is all part of the standard calculation, not part of the optional calculation. So the table for ranges on page 74 and the table for dryers on page 73, those do not belong to the optional method. You do not use those for optional method calculations.
Okay.
Okay. So I've seen them play tricks with that where they give you a whole bunch of multifamily dwellings and they give you a whole bunch of dryers or ranges in one of them, but then they turn around and tell you not to use the optional method of calculation and they ask you to calculate the dryer or the range. Well, I mean, that would be no different than me giving an example of 41 dryers or 23 dryers or 23 ranges or whatever. I mean, you just use the tables that are on page 73 and 74 respectively for standard method of calculation. That probably made no sense to you, but it's okay. I'm recording this and I'll post it on YouTube and you can watch it again and again and again.
Okay.
You're going to be a star. Let me ask you this. When is your test again?
Tomorrow.
Oh, great. Okay.
Yeah.
You won't be able to watch it again and again. Hopefully you won't have to.
No.
What specifically, service calculation-wise, do you want me to talk to you about or give you an example of?
It's mainly the residential, like
Okay.
with the 3,000
Okay.
and adding about all that.
So let me list down the articles first, kind of talk about that first, just so 220.12. There's also a table, 220.12. So that's kind of our step one if we're talking about stuff. And if you look in your textbook, I had like a breakdown of kind of a recap of all of these articles and stuff on one of the pages in the back. If you look in the table of contents, it should tell you what page it is. It's like a recap. It's labeled recap or something. But at any rate, step one is basically the lights and just all of the general purpose receptacles. Just going to call it GP. Sometimes on the test they refer to them as 15 amps. I mean, they don't always have to be 15 amps. They can be 20 amps. But basically the general purpose plugs, the non-specifically specified circuits in a residential dwelling. And I say that because step two is effectively the other required outlets or power circuits. And you'll find those in 220.52A and B. In 210.11C, 1 through 5, there were some circuits that they said you have to have. So 210.11C, you don't have to go there, but 210.11C basically says, look, in a residential dwelling, you're going to be required, in that panel that's in the garage, you got to have 5 20-amp branch circuit breakers, 2 of them for the appliances in the kitchen, 1 of them to go into the laundry room for the washing machine, 1 of them going to the bathroom or bathrooms combined. They can all be on the same one, but you have to have at least 120 circuit for that bathroom power circuit. And then now, new for the 2017, the garage has to have its own 20 amp. So those 5 20 amp physical branch circuit breakers, right? But then when we come back over here to 220.52, when we're talking about calculating the feeders or the service for the building, for the dwelling unit, we only calculate the 2 that are in the kitchen and the 1 that's in the laundry. We don't care anything about the 1 that's in the bathrooms, the 1 for the garage, okay? Or the 1 for, yeah, that's it, okay? Now, in .52, it says that each one of the ones required in 210.11C 1 through 5 that are in this calculation, which are the 2 kitchens, each one of those is 1,500 VA, right? And then the 1 for the laundry is also 1,500 VA. So I'm basically just telling you all that just so you know where it's at. What that boils down to is basically all of that means that effectively step 2 is simply going to be, you guessed it, times 4,500 VA, or excuse me, not times, plus.
So you just add that in there.
Yep. I don't care if it's mobile. I don't care if it's portable. I don't care if it's on wheels. I don't care if it's on blocks or a pier and beam or concrete. If it's got a pot, a cot, and a hot, some plate or a cot, a pot, and a hot, something to cook with. If it's somewhere somebody can sleep in, and we call it a dwelling unit, you're going to have that 4,500 VA. It's just everywhere in the code book that there's any residential calculation. It's always 4,500 VA plugged in there for that. Okay, so let's call that the receptacles that are the 20 amps. Now you can see why we kind of refer to the other ones as the 15 amps, because we specifically specify 20 amps somewhere else. Okay, now that's it. I mean, I don't really have to worry about a range, a dryer, anything else, because air conditioning, heating, I mean, they could have fans and they could have gas heat, right? Mm-hmm. I don't have to worry about it. But if they list them, then I have to calculate them. Now, I do take a D-rate. In the standard method, I'm going to do both of these steps together, and then I'm going to go to 220.42. There's a table back there, and I'm going to D-rate that step. Okay? So I want you to write down those three table numbers. Basically, what I'm looking for is the table that's 220.12, the 220.52 A and B, which is not a table, but it's an article to write down, and then 220.42. Those are the three things I want you to just jot down because those are the ones to remember. Okay.
Okay.
Now we're gonna do a quick example. Let's say that we had a dwelling unit, and they told me that the calculated square footage was equal to 3,200 square feet. Okay. And they want to know the minimum service required, or minimum demand on the feeders would be the better way to say it. Minimum demand on the feeders. What that means is they're asking me to calculate the D rate. Okay? So I'm going to go, okay, 3,200 square feet. I go to the table on page 71. Two? I meant, yeah. The table there for dwelling unit says 3 VA per square foot. By the way, all of this goes out the window in the 2020 edition. The LEDs have hit. Now we've got a whole different way of calculating this stuff, so you only have to remember this for 6 more months. Or at least if you pass this test, and then we'll have another relearning because it'll all be different. But at any rate, that's the way it is for now. That's going to give me 9,600 VA, right? That's a connected load. I haven't derated any of it, right? So that's step one, into step one. Next thing I do in step two, I go, okay, remember, step one is all my lights and the 15 amp general purpose receptacles, right? But I have to figure out those 3 required circuits that I got to throw in there. So I'm going to end up in step 2 going back and taking that 9,600 VA, and I'm going to add 4,500 VA to that. Got to do it every time. That's going to give me a total connected load of 9,600 plus 4,500 VA, 14,100. Okay? Now, let me ask you. When you come home, does your wife have your favorite meal on the stove, electric stove? Does she have a beer sitting in an artificial chiller over there by your easy chair recliner with the little vibrator thing going for you so you can sit down and get a relaxation? And the TV on for you, the air conditioner lowered down, maybe a little beer fridge next to you so you can help yourself to your favorite cooler?
No.
So this number here is that imaginary world, and that ain't never going to happen for blokes like you and me. So
Right.
We got to derate it. We got to get it into a real world, realistic expectation. Well, how do I do that? I go to the table on page 43, 2, 5, 4.
72.
220.42.
That's 72.
Okay, that's the one on the right-hand side down the right-hand corner. What that table says, it says, okay, take that 14,100 that you just calculated. Remember, that's the connected load, so we got to derate it into a demand factor that will give us the demand load. So that's what we're getting at. On that table, it says dwelling units at the very top. 0 to 3,000 VA, I have to keep 100%. So they're saying that of this 14,100, the first 3,000 of it, I'm not allowed to derate at all. So I'm going to get it out of my way, and I'm just going to put it over here in my bank. I'm going to keep all of it, so I'm just going to keep it, put it over there to the side. What is left over is 11,100, and that amount right there, I'm going to take the second row, which says 35% is what I'm going to keep of that number. That's a big discount. 65% is going to get whacked off and thrown in the trash. I'm going to keep 35%. That's my derating factor for the portion that I'm allowed to derate. So 14,100 minus 3,000 is 11,100 times 0.35 gives me 3,885 VA left over. That portion then comes over here in my kitty, and I'm going to add that to the 3,000 that I couldn't derate earlier. And then I'm going to combine those two together for a demand load of 6885 VA. That's the demand, minimum demand on the feeders for a single family residential dwelling, no other loads considered. Okay.
Okay.
They tell me I've got 4 bathrooms. Great. That's nice to hear. Doesn't change my calculation a bit. I've seen them do that. They give you all the square footage, tell you got 4 bathrooms and yada yada. So it doesn't
matter.
that didn't come into my calculation because remember the bathroom circuit, I'm required to have one. I got to have a 20 amp, but I don't. There's no calculation for it, so that's just extra information. Okay.
Mm-hmm.
So just be careful of little stuff like that. If it's not the 2 kitchen appliances or laundry circuit, it doesn't blow my skirt up at all.
Okay.
Now remember, don't forget. In 230 and 225, I think it's 230 I want to say .79 or somewhere in that area. Don't quote me on that, but there's a minimum service size that we can't have anything less than for a single family dwelling 100 amps.
Mm-hmm.
So this 6885, if you were to divide that by 240 volts, which is what we would do if we were trying to calculate the ampacity of it, I mean, that's obviously going to be way less than 100 amps. But remember, they asked me for the demand load on the feeders. That would be the minimum demand load, 6885. If they asked me for the minimum service for residential dwelling, given all those factors, 100 amps would be my answer because I can't have less than that.
Right.
And remember, feeders for residential dwellings go to page 800. Don't use page 150 to size feeders for residential dwellings. Okay?
Okay.
All right, now, what do you do if you have a calculation that resulted in, let's just test you for a second. Let's say you had 3,905 or 39,500 VA, sorry. That was your connected load for residential dwelling. What size, and you're going to have to tell me because I don't have my book in front of me, what size aluminum feeders would I have to have? And then what size minimum grounding electroconductor would I have to have? And what size minimum neutral conductor would I have to have if my neutral calculation was less than the table value that's on page 119? So we're looking for minimum aluminum, looking for minimum neutral. Remember, the neutral is a grounded conductor, right?
Right.
The official term for it. And then, what's my minimum GEC size? All right. How do you calculate that? Where do you go? Where do you get started?
So would you divide it by your voltage?
Absolutely. What's the nominal voltage for residential dwelling?
240.
All right. So I'm going to divide that by 240 volts. That's my first step because I need to subtract the ampacity out of that, right? So 39,500 divided by 240. Great. I messed that up. 39 is what I get for trying to be funny. Divided by 240 gives me 164.58 amps. Now, is that a standard size overcurrent protection device?
No.
Go to page 95 and tell me what the next standard size up from that would be. And I have to round this up every time to the next standard service.
175.
Right. I'm going to use 240.6, the table there, for standard services, even though that's standard breaker sizes. It's all the same thing, right? So 175 amps. That's correct. So I'm going to have a main breaker or a main fusible disconnect, however I set it up. I have a 175 amp main. Now what do I do to size the aluminum conductor?
Go back to 119.
No, you're looking for the actual feeder size. That's the page 800 I would mention. So if I'm sizing the aluminum feeder, I'm going to go to page 800. I'm going to use page 800, not page 150, because page 150 is not for residential feeders. Page 800's got that little table back there that used to be way back in the front of the book, but they put it back.
Right. 1 aught.
That's for aluminum?
That's for copper. It's 3/0 for
All right.
aluminum.
3/0 aluminum. So that's answer number one. I'd have to have a minimum 3/0. Now, 3/0 aluminum is the wire size I have. Size of GEC first. That's the easy one. So that is on page 116. That's the GEC stuff. That's your service ground, your one before the breaker size. Remember, that's 3/0 aluminum. I'm not asking you for an aluminum GEC. I'm just asking for GEC. So you're going to answer in copper, even though I've got aluminum feeders.
It'll be number 4.
Copper? Huh? Yeah.
Copper, yeah.
Okay. So I have a number 4. All right. Now, what about that pesky neutral? Where do you go for that?
That's one you
look on page 119. Look on page 119 real quick and tell me what is the label of that table, that 250.102C1. It's the first word. Grounded conductor. That table, not only do we use it for bonding or sizing service, like supply side bond jumpers, it's also a minimum size neutral table. Okay, and in this case, I said it real fast. What I was trying to say is, let's just say your calculated neutral load was smaller than that table. So in other words, that table then would be the minimum size. It's either going to be a calculated size or that table, whichever's bigger. In this case, we're saying the calculation would be a smaller wire size. So what do you have on that table there for an aluminum?
4/0 or 4, number 4.
So it's the same size. So really not any discount for that. I mean, your neutral and your GEC would be effectively the same number 4 copper. Basically the same table, right?
Right.
All right. Well, there you go. That's all I'm giving you. You're done. You can't read nothing else out of me. Is that helpful?
No, that really is.
Okay. You got any specific questions for me before I kick you out and go eat supper?
No. I think that really helped.
I hope so, man. Listen, remember that test. Have you taken it before already?
Yeah, I've taken it twice already.
All right.
I missed 8 questions too many on my calculations last time. So.
Okay. I mean, don't let it worry you. I mean, it's stressful. I mean, I know that I mean, you got a lot riding on it, and it's tough to go take a test like that. Remember that, you're in the driver's seat as much as you want to be. So when you first walk in the door, be the last person to get in that line so that you're the last person they have to deal with. It's worth it because, number one, it forces you to kind of catch your breath a little bit. Number two,
right,
you're the last one in the door, so they're not showing off for anybody. Okay. They're going to give you that boogie board. Nothing hurts to ask for another one. If they say no, ask them for paper. If they say no, at least you tried, right? They give you a calculator. They give you your plans, your prints, and they give you your code book back. Walk in the door, sit down at the table. I mean, don't enter your Social Security number. Just take the plans and start looking at them. And if they start knocking on the window, then enter your Social Security number. But try to milk as much time in that front few minutes as you can. And then if you do enter your Social Security number, those pre-test questions they give you, you're not required to answer them. You can just let it – I mean, you can enter your Social Security number and hit start and then just let that sit there and then open the plans. Give yourself as much of that time frame as you can. You get like 15 minutes to take that pre-test. And it doesn't count against you on your real test, so let that clock run. Doesn't hurt. You know what I mean?
Mm-hmm.
Kind of get yourself situated. Go over that table of contents in the front of your code book and kind of just give yourself one last remembrance of what's in Chapter 2 and what's in Chapter 3 and so on and so forth. That's the way I always kind of start my test times, just to kind of give myself a little bit of time to relax and experience, right? And then when you start doing the math, go through every one of them with that code book closed and just read through them and see how many of them are calculations for motors and how many are calculations for services and how many are ground wires and bonding jumpers. And I mean, give yourself a feel for what's on there and then go back through there and try to answer all the grounding tables, all the ones that were one table or another, just try to answer them all back to back. So what you do is after you've kind of gone through and read them all, go back to the first beginning of them or wherever you're at and then go, okay, I saw another grounding table question 2 more down. So I'm going to answer this one. But before I turn my code book, I'm going to flip through those 35 questions until I find the next ground wire and answer them all together. Because if you do them in clumps like that, you'll catch yourself remembering stuff you could have, should have remembered the first couple of times. So I like doing them that way instead of trying to do them separated by several other calculations, because you're flipping back and forth the book and you don't remember really what you're doing from one to the next.
That makes sense.
So it's the best advice I can give you.
Okay.
All right.
Well, I appreciate it. Thank you.
Hey, last note on that, on the stuff for the NEC code calculation, or the NEC part, right? The word questions for the code lookup stuff. Don't get stuck on anything. If you can't find it within a minute or two, guess and move on. Okay.
Okay.
Get stuck. All right.
Okay.
All right. Call me tomorrow and let me know how you did. All right. I'd like to know.
All right. I'll let you know.
Okay, buddy. Good luck.
All right.